So in our previous class, okay, we started to look at this concept called heat capacity. Okay, and then after that we talked about specific heat capacity. Okay, so heat capacity is how much heat you need to raise the temperature by 1 degree Celsius. Okay, of any material lah. Okay, and it can be any mass as well. Okay, so it can be, for example, if you say you want to panaskan this one, you want to raise the temperature by 1 degree Celsius. Okay, how much heat you need. But specific heat capacity is specific to 1 kilogram. So we have to, we bring it down a little bit because heat capacity changes with different mass. Okay, for example, if the bottle that I showed you just now, if it's just an empty bottle, the heat capacity will be different than if it was a bottle that is filled with something because there's more things inside lah. Okay, so heat capacity changes, but specific heat capacity is a constant. It doesn't change. Okay, that's why specific heat capacity is an important marker for us to know how much heat we need. Okay, if we want to increase a certain material punya temperature by 1 degree Celsius. Okay, and actually there are two experiments that you are supposed to be doing, but experiments have to be done in a lab. I can't really do a virtual experiment for this because I think it's so important that you do this lah. So maybe when we go back to school, maybe if you go back to school, okay, although I highly doubt it lah, but if you go back to school, one of the first things that we need to do is to do this experiment lah. Okay, we will have to modify it a little bit so that it fits, so that we can use our own stuff to do this experiment. But I think it's a good experiment for us to do to determine two things lah. One is to determine the specific heat capacity of water. Okay, the specific heat capacity of water actually is 4200 lah. Okay, it's 4200 joules per kilogram per degree Celsius. Okay, that is the specific capacity. Means 1 kilogram of water needs 4,200 joules of heat energy in order to increase it by 1 degree Celsius. Okay, but how do we determine it? So how do we determine any specific capacity? If it's water, then we will use this setup lah. Okay, we will have a beaker. You put the water inside, then you measure the mass, and then you fill in the water in the beaker until 3/4 full. Then you take the reading of the water on the mass. Okay, again to calculate the mass of the water lah. Then you take the temperature reading initially, and then after that you start to heat it up. Okay, so this is an immersion heater. Okay, this is what an immersion heater looks like. It's basically something that when you connect electricity to it, it becomes hotter. And when it becomes hotter, it will make the water hotter. Okay, so the heat energy over here is transferred to the water and the water will start to rise in temperature. After 5 minutes, okay, we turn off the immersion heater and then we take the highest reading of this thermometer. Okay, and then after that, we do a little bit of calculation to find the specific capacity of water. We won't be doing this today, okay, partly because this is not what I want to do today, but I just wanted to show you this experiment lah. And I hope that we get a chance to go back to school so that we can do this experiment. This experiment is very important. I don't think it's fair if I just skip it and then okay, tak payah buat lah. No, you must do this experiment. Okay, the second experiment is the same, okay, except that this is to determine the specific capacity of aluminium. Okay, not the American pronunciation, aluminium. Okay, it's like lazy. Okay, aluminium. Okay, so aluminium, the specific capacity almost the same. Okay, even the steps are about the same now. You take the initial temperature, okay, then you start to switch on the immersion heater. Okay, you turn on the immersion heater, turn on the pemanas lah. Okay, lepas tu dia akan menjadi panas and you after 5 minutes, you turn off the heater and you take the highest reading possible. Okay, there's a reason for this. Okay, then after that you do a few calculations to calculate the value of C. Okay, I can't remember what the value of C is lah, but basically the setup is the same. Okay, almost the same except that this one you use an aluminium block and usually the aluminium block is already 1 kg lah. Okay, this one is found in the lab. Okay, our lab has quite a lot of aluminium blocks and usually it's about 1 kg, 1 or 2 kg. Yeah, so this is 1 kg lah. In this setup, is 1 kg. And Uh, and since it's 1 kg, it's much easier. It's a little bit easier than the water one. Okay, this one, when people do this experiment, they tend to get the value that is quite close to the original value. If you do the one with the water, usually people will get very far away. Okay, they won't even get anywhere near 4,200. Usually it's much less lah. Okay, for a number of reasons, which only when you do the experiment, then you will understand, oh yeah lah, actually why is this, why cannot reach the 4,200? Okay, it's for so and so reasons. Okay, so these are two experiments that we will only do if we go back to school, and I kind of need you to remind me that we need to do this experiment. Okay, so if I forget, okay, please remind me, sir, we have to do the heat experiment. Okay, then I will make sure that you'll at least get to experience to do this experiment, because it's a very important experiment to do. Okay, I think you should do it. Okay, but today our focus, first of all, is if you turn to your module, okay, we're going to do a little bit of problem solving. Okay, problem solving that uses this formula. Okay, Q equals to MC theta. Remember, Q is the amount of energy, amount of heat energy, okay, that is required to raise the temperature of how many kilograms with different specific heat capacities. Okay, so this is our job for today. I think it's on page, oh well, I don't know what page is this. Page 88. Okay, page 88 of your module. Okay, if you don't have the module, then take a look at the soft copy version that I gave you lah. All right, so first thing that we must understand is that we cannot actually create heat energy. If you think about it lah, okay, we cannot create heat energy. Heat energy is always a byproduct or it's always converted from another form of energy. Okay, think about it. We never can create one. We always use something else to transfer to heat energy. For example, when you light a candle, okay, or when you light a match, actually what is causing the heat energy is the chemical from the matchbox and the matchstick. So we're changing chemical energy to become heat energy. Okay, you don't actually create fire, but you use other methods. Okay, you use other methods, other forms of energy to convert to heat energy. Okay, and this year for all of you, these are the three most important ones. Okay, these are the three most important forms of energy that we use to create heat energy. For example, electrical energy to become heat energy, this is the most common. We use this every day. Electric heater, iron, your hair dryer also works around the same principle. Okay, you think it become hot by itself? No, it become hot because the electrical energy convert to become heat energy. Okay, this is something that a lot of people cannot seem to grasp. Okay, a lot of people cannot seem to grasp because think about it, you cannot create fire. You cannot create heat energy. All you're doing is just changing one form of energy to another form of energy. And people will be like, get out of here, you're talking crazy, you're talking nonsense. It's not nonsense, it's scientific fact. Okay, you're just converting energy, okay, from one form to another. Okay, so electrical energy is actually counted as power times time. Okay, so every single electrical appliance that you have has a certain power. Okay, and then this time, I want you to make a note there, the time must be in seconds. Make sure that your time is converted to seconds before you calculate the total energy. Very important. Okay, second one is potential energy. For example, an object that falls from a high position. Okay, you drop a stone from somewhere very high. It has potential energy, and as it moves down, it's going to be converted to heat energy also. So potential energy punya formula is mgh equals to mc delta theta. Okay, h is height. Okay, in meters. Make sure that it is in meters. All right, and then lastly, kinetic energy. Okay, kinetic energy, it usually, when it's converted to heat energy, is usually a moving object that is being stopped due to friction. Okay, because when something moves on the ground, there's always going to be friction, and the friction there causes heat energy. So that kinetic energy is converted to heat energy, And since the conversion we assume is 100%, so we say that kinetic energy is half mv squared. V is for velocity. Okay, this is something that we learned in chapter 2. So half mv squared equals to mc theta. Take a look at the heat energy formula, guys. Heat energy formula doesn't change. We are still at mc delta theta. Okay, it's just that we cannot create heat energy lah. Okay, this is the fact of the matter. Okay, so let's take a look at a couple of exercise questions, because this is one of the main things that I want you to do today lah. Okay, and I want to give you a word of warning. You need to be able to copy this very, very fast. Okay, if you're going to copy, I mean, if you've already answered, good for you, and you just want to check, can. But I assume, and I'm assuming that a lot of you actually haven't even looked at these questions. So you're going to be doing a lot of copying, and you need to do this very fast. Okay, if you can't catch up, it's okay. When I post up the video again later on YouTube, you can pause the video and you can take a look at it. Okay. All right, so an electric kettle is rated now 1000 watts. Okay, 1000 watts refers to its power. Okay, so when you're given this power, you immediately know that you're talking about this particular one. It is not a formula, guys. It's just a combination of two powers. Okay, so we're talking about PT equals to MC delta theta. So calculate the quantity of heat generated in 5 minutes. Okay, remember 5 minutes needs to be changed to seconds, because I said that power, when you calculate, the time must be in seconds. So this is what you will get. You change this 5 times 60 into seconds, then you multiply with the 1000 watts. So the amount of heat it generates is 300,000 joules. Okay, then you use that to calculate the rise in temperature of 750 grams of water if the electric kettle is switched on for 5 minutes. Specific heat capacity is 4,200. Okay, first of all, 750 grams needs to be changed to kilograms. So this has to be 0.75 kilograms. Okay, so we need to make sure that all our units are in order. Okay, these are rules these are rules that you have to follow. Okay, yes, it is very troublesome. Okay, I admit okay, all these things are very troublesome. Why don't they just give us this one in seconds? Why don't they just give us the thing in kilogram? Why must we convert this? Okay, I have no answer to that but I feel that if you're willing to stand in front of McDonald's for 2 hours to buy the BTS meal, I think changing 5 minutes to seconds is totally not a problem. Okay, so priorities, people, priorities. Okay, so this is how it will be like. We use the 300,000 that we got at the very beginning. Okay, kasi equals to MC delta theta. This is 0.75 because we've converted it to kilograms. 4,200 is already given, and they are asking to count the rise in temperature. Means the water, originally we don't know how many degrees it is okay, we don't know how many degrees it is, but we know that it rises at 95.24 degrees Celsius. Sorry, there's a Celsius missing over here. Okay, so rise in temperature is 95.24 degrees Celsius. Means we provide 300,000 joules of heat to it. It's going to rise 95.24 degrees Celsius. Okay, dia punya kenaikan adalah 95.24. Doesn't mean that it's going to reach 95.24. It actually reaches more than that. Okay, room temperature water is about 27 degrees Celsius. Okay, room temperature lah. So if you panaskan and dia increase 95.24, okay, how much is this going to be? It's going to be let me see, 122.24 degrees Celsius. Okay, the water is going to reach a temperature of 122.24 degrees Celsius. 27 plus 95.24. Okay, so this is what this 95.24 means, increase in temperature. Question number 2. 200 grams of water with a temperature of 40 degrees Celsius is mixed with 800 grams of boiling water. Okay, if there is no heat loss to the surroundings, what is the final temperature when the mixture of water achieves thermal equilibrium? Okay, this is a thermal equilibrium situation. Okay, so write down here, thermal equilibrium situation. Now, in a thermal equilibrium situation, we need to think about this now. Originally, we have 200 grams of water at 40 degrees Celsius. It's going to be put inside, okay? Oh, sorry. It's going to be mixed with 800 grams of boiling water. Boiling water is at what? It's going to be 100 degrees Celsius, bahkan. Okay, so this is going to be put inside here. So think about it. When you put inside there, what is going to happen to this temperature of the 200 grams? The temperature is going to increase. Kan? Manakala, the 800 grams of water, the temperature is going to decrease. Okay, but because this is a thermal equilibrium situation, okay, I'm going to use different colors lah. Okay, the blue color represents the 200 grams. This will be MC delta theta blue. Okay, and this will be, let me see, green. Let's use green now. MC delta theta for green. Okay, so in this case, okay, for the blue color, it will be like this. Okay, M is 0.2. Why is M 0.2? Blue color. Why is M 0.2? Because it is 200 grams converted to kilograms. Okay, the C we don't need to know because it's the same. Okay, for both, both is water, but this is the delta theta. It's going, these two, okay, this is going to increase until it becomes theta. Okay, it becomes a same temperature. This is going to decrease until it achieves the same temperature. You all did this when you were doing the PBL. Okay, what is the concept of thermal equilibrium is they will both change in temperature until they reach the same temperature. And since this is an increase in temperature, we will calculate it as theta minus 40 because the final temperature is theta and the original temperature is 100. On the green side, however, okay, on the green side, once again, we see that the 800 has changed to 0.8. Okay, we maintain the C as it is, doesn't matter because the C will be cancelled out. Okay, the question is, why is this 100 minus theta? Because originally it's 100 and it cools down. Since it cools down, it's going to cool down to a smaller temperature. Okay, smaller than 100 lah. So this order is very important. This is theta minus 40 because this one is temperature increase. This one is 100 minus theta, because this is temperature decrease. Okay, this temperature is going to decrease. Okay, so you calculate, you will get theta equals to 88 degrees Celsius. Means when you mix both this water together, they're going to reach a thermal equilibrium temperature. When they achieve thermal equilibrium, they will have a common temperature of 88 degrees Celsius. Okay, so in a thermal equilibrium situation, you're going to have this one, MC delta theta blue equals to MC delta theta green. It's just that the M and the delta theta will be different. Okay, it will be written much different. Okay. Question number 3. Just check and see. Okay, question number 3. How long does it take for an immersion heater of 12 watts? Okay, this is 12 watts. So you kind of know that this is going to, Okay, so how long is the time? Okay, when you see the wattage here, you know that we're talking about this formula again. Okay, because this is the only one that involves wattage. Okay, power lah. So PT equals to MC delta theta. Okay, so PT equals to MC delta theta. So raise the temperature of 200 grams of water. Guys, 200 grams needs to be converted to kilograms. And when you convert it, it becomes 0.2 kilograms. Okay, raise the temperature by 5 degrees Celsius. This is our delta theta, 5 degrees Celsius. They don't tell you how much is the beginning and how much the end. All I want to know is just just increase by 5 degrees Celsius. So we have all the information. What are we asked to find? How long? How long is time? Ini yang kita mau cari. Do we have the power? We have 12. Do we have the mass? We have 200 grams changed to 0.2. Do we have the C? We have 4,200. Can we find the time? Can, very easily done. Okay, it will be 350 seconds. You can change the seconds to minute if you want. 350 seconds equals to how many minutes? Almost 6 minutes, 5 point something minutes, I think. 50 divided by 60. Yeah, 5.83 minutes. Okay, you can write it as 350 seconds or you can write it as 5.83 minutes. It's totally fine. Okay, not a problem at all. A lead bullet moving at a velocity of 200 meters per second hits a sandbag. Okay, and this is normal lah. Okay, when you see velocity, you kind of know that we're talking about this formula. Okay, the one that involves movement. Okay, involves kinetic energy. So you want to be able to take a look at this lah. Okay, half mv squared, okay, equals to mc delta theta. Temperature of the bullet rises by 50 degrees Celsius. Assuming all the kinetic energy is converted into heat energy, calculate the specific heat capacity. We want to find the value of C. Okay, so the first question first, where is the M? Where did the mass go? Okay, because they are the same mass, the bullet lah, so the mass actually already kena potong. So we don't have to worry about the mass. So in the end, we have C theta equals to half V squared. V is the velocity given 200 meters per second. Okay, and then the C is the increase in temperature. The delta theta is the increase in temperature 50 degrees Celsius. So you calculate, you get C equals to 400. Make sure you get the unit correct. Joules per kilogram per degree Celsius. Okay, so once again, actually the calculation is pretty easy. Okay, it's just understanding which situation requires which form of energy. Okay, remember kinetic energy is half mv squared. Electrical energy is P times T, power times time. Okay, and then potential energy is mass times gravity times height. Okay, and remember gravity is 9.81 okay, meters per second. So, and all energy, okay, the unit for all energy is the same. It's always joule. Okay, the standard unit for energy is always joule. So it doesn't matter whether it's heat energy, kinetic energy, gravitational potential energy, electrical energy. Power times time is also joule. mgh is also joule. Half mv squared is also joule. Okay, so that's a good shortcut to remember. You don't have to remember half mv squared means kilogram, meter squared, second, tapaya. Just change it to joule. Okay, it's all well and fine. Question number 5. A lead ball of mass 320 grams. When you see this, immediately convert to become 0.32 kilogram. No need to think. Okay, we want to use standard form. So we never use gram one. We always use kilogram, or something like that. It's dropped from a height of 12 meters. Okay, situation where the ball drops. If the ball is dropped, then we're talking about mgh, potential energy, okay, equals to mc theta. Assuming that all the energy of the ball goes into heating the ball, means the potential energy changes to become heat energy. Okay, calculate the change in temperature. Change in temperature is represented by which symbol? Delta theta. This is what we want to count. Okay, so specific heat capacity is already given. This is C. What else is given? Oh, we need to have the G value lah. Okay, now there is a mistake in this guys. Okay, there is a mistake in this. Okay, first of all, this M, once again, the mass will be the mass will be cut off. Okay, but in this example guys, we don't use G equals to 10 anymore. Okay, we use the value of G equals to 9.81. Okay, so take some time and calculate this, please. 9.81 times 12 equals to 128 times theta. What should this answer be? 0.9196675. Walao. Okay, 0.9197 lah. Okay, degrees Celsius. I'm just 9197, yeah. Okay, 9197 degrees Celsius. Okay, so there's a mistake in this slide now. We don't use 10 anymore, we use 9.81. Okay, the standard value of the gravitational acceleration. Be careful with this, people. Okay, be careful with this. The value of G is actually 9.81 and we use 9.81 in physics now. Okay, so these are some example calculation questions which if you read the situation, then you just need to know which energy to use. Okay, because I know, okay, because I said that, okay, original formula is Q equals to MC delta theta. But the problem is our Q can come from different sources. Okay, different sources. It can come from electrical energy, it can come from kinetic energy, it can come from potential energy. Okay, so as a start, these 5 questions I think are good examples for you to do when you do your exercise later. Okay, all right, next part. Guys, this next part's got a lot of things to copy. Be ready. Okay, we're going to need to look at a few applications of specific capacity in real life. Okay, actually, we more often than not, we use the concept of specific capacity in a lot of situations. Okay, every day. Okay, example, water acts as a heat reservoir. So the first thing that we need to understand is this. Okay, the characteristics. Things with small specific heat capacity. Okay, things with small specific heat capacity heats up and cools down faster. Very important thing. If you have a small specific heat capacity, okay, you will become hotter faster and you will become cooler faster. Okay, so this one you can copy in this table over here, the part that says characteristics. Okay, so small value of heat capacity will heat up and cool down faster. Okay, and it is sensitive to the change in temperature. A little bit of change in temperature, okay, done already. Whereas things with big specific heat capacity takes a very long time to heat up and a very long time to cool down. Okay, there are good and bad situations in this, and we're going to look at both of these. And it can absorb a large amount of heat without getting hot. Okay, so for example, water okay, acts as a heat reservoir. Okay, if you want to cool things faster or if you want to store a lot of heat, we use water because it can absorb a great amount of heat before it boils. The specific capacity of water is 4,200 joules per kilogram per degree Celsius. Means you want to kasi naik 1 kilogram by 1 degree Celsius, you need 4,200 joules of energy. That's a lot of energy. Okay, 4,200 joules is a lot of energy, and water is able to absorb that much amount of water. Okay, that's why it takes a very long time to boil water if you're going to use the gas stove. It's not like you just turn on the fire, poof, okay, boil already. No, you still have to wait for a long time. Apalagi kalau dia banyak kilogram, many kilograms of water. Okay, if it's just to cook Maggi, then obviously it'll be faster because the mass of the water is very small. Okay, but if let's say you want to boil a jug of water, takes you maybe an average of 7 or 8 minutes, 6 to 7 minutes depending on the power of your water kettle also. Okay, so we find that one of the most common uses for water is as a cooling agent in a car radiator. Okay, your car engine gets hot very easily. Okay, because there's a small specific capacity. And so the radiator there's a lot of water because the function of the water is to absorb the heat from the engine so that your engine doesn't become too hot. Okay, so this is the same thing. Okay, it's the same thing except that we just want to see this. Small value of C means very fast increase temperature. Okay, if it's a big value of C, then it's a low increase in temperature. Okay, now one of the important things okay, is in a cooking pot. Okay, a cooking pot we find that the base has a copper base because the specific heat capacity is low. Okay, low specific capacity, the reason will be so that it becomes hot very quickly. Okay, this enables the quick cooking of the food in the pot. Nobody makes a pot which is made of plastic. Okay, number one, because plastic melts. And number two, because plastic has a very high specific heat capacity. Okay, high specific capacity means the plastic is going to take a very long time to get hot. Or worse, nobody makes a pot that is made of wood. Okay, because although wood is nice and very rustic and everything, but because it has a very high specific heat capacity, it takes a very long time to become hot. Okay, orang sudah habis makan, kau masih lagi, menggoreng bawang. Okay, so, we use things with low specific capacity for the body of the pot. Okay, number two, it has a high density. Okay, so that the heavier base ensures that the pot is stable and will not topple over. Okay, so in your module, okay, guys, in your module, this one, specific capacity is low, and then this one is the reason. Okay, high density, and then this is the reason. Okay, if you want to copy down lah. Okay, now look at the body. Look at the handle. Okay, the next part is the handle. The handle will have a high specific heat capacity. Okay, so that it is a poor heat conductor or heats up. It heats up slower. And that's what we want. Okay, imagine if your handle is a metal handle. You pegang the handle, it become very hot very easily. We don't want that lah. We want to be able to hold the handle without using any glove or anything lah. Usually I also use glove lah. Okay, but generally the body of the pot becomes hot faster, but the handle takes a long time to get hot. Okay, so the body will be aluminium body because it has a low specific capacity and it heats up quickly. Okay, all these are reasons over there. All right, next. Oh, sorry, wow, cooking pot. So the wooden handle, sometimes it's wooden handle, sometimes it's plastic handle. I think most of the time we use plastic handle right in our cooking pot. Okay, it has a large specific capacity so that the handle will not become too hot when the heat is absorbed. Okay, it is a poor conductor of heat. Okay, aluminium, sorry. Okay, aluminium body. Okay, aluminium body, it has a relatively low specific capacity, definitely lower than wooden handle, maybe a little bit higher than copper base. Okay, the pot becomes hot quickly. Low density so that it will be lighter, does not react with the food in the pot. So you notice that actually the body as in this lah. Okay, the body is aluminium, but the base di bawah sini, okay, the base is made of a different material. Okay, which in a good pot, okay, it is made of copper lah. Okay, a good pot will be made of copper. But because both copper and aluminium have low specific capacities, so you get hot faster. The handle is the most important thing. Okay, handle, we want it to be a different material, wooden or plastic, okay, if you want, because we want things that are big specific heat capacity. Because big specific heat capacity will take a long time to become hotter. Okay. All right. Next, another application of this is sea breeze and land breeze. Okay, have you ever been to the beach in the daytime and in the nighttime? You'll find that in the daytime, standing on the land, okay, obviously it's much hotter lah. Okay, but in the nighttime, when you stand in the sea, it's hotter, okay, than on land. Okay, and this happens because of the movement of sea breeze and land breeze lah. Okay, so sea breeze happens during the day. And we say sea breeze because the breeze comes from the sea. This is, dalam bahasa Melayu, this is called bayu laut kah ini? Yeah, bayu laut. Okay, so bayu laut datang dari laut lah. The sea breeze comes from the sea. Duh. Okay, so the movement of the cool air happens from the sea, goes to the land. Because during the day, the heat is absorbed by the land and the sea. Both lah. Okay, both the sea and the land absorbs the heat. But since the sea is water, it has a high specific heat capacity. So the increase in temperature here is smaller. Okay, the temperature increases much smaller. This makes sense to us. When you go to the sea in the daytime, the sand is very hot and the seawater is generally cooler, okay, compared to this one. Because land over here has a small specific heat capacity. Okay, so land small specific capacity becomes hotter faster. Okay, it becomes warmer than this one. Sea has a high specific heat capacity. Okay, it becomes hotter slower. Okay, the temperature increase is slow. And so because of this, the warm air above the land will rise. When the warm air above the land rises, okay, what will happen is the cool air will move from the land towards the sea. Okay, 1, 2, 3, 4, 5. This is the step. This one must remember lah. Okay, sea breeze and land breeze is probably the most important application of this, which a lot of people always fail to remember. But it's very easy to remember because now if you've ever gone to the beach, you will know this. The only thing that now makes it a little bit difficult, technical, is step number 4, step number 5. Okay, warm air always goes up. Okay, warm air always rises. Okay, and then cool air, okay, will always move towards. So there is no air already lah. Okay, in this, because the hot air all go up already, right? So there's no air. So the cool air comes here. Cool air comes here, becomes hot, goes up. Okay, when it goes up, then it goes all the way here. It becomes cold, and then it comes in, and so you get a circular movement. Okay, go to the sea, become cold. Go to the land, become hot, go up. Become hot, go up. Become cold, go down. Okay, become cold, go down. Then it gets blown into the land which is hot. Become hot, go up. After become hot, over up there it becomes cold, so it comes down again, and it goes in one full circle like that. Okay, sea breeze. The other one is land breeze. Land breeze is the other way. It is the movement of the cool air from the land to the sea. Because at night, what happens is the land loses heat faster. Smaller heat capacity, easy to terima panas and easy to let go of the panas. Okay, smaller heat capacity. Okay, so land loses heat faster than sea at night due to its low specific heat capacity. Sea is hotter than land. This is true. Okay, at night now, when you go into the water, okay, generally it is still much hotter than the sand. Okay, because the sea water takes a very long time to menjadi panas, tetapi dia take a very long time to menjadi sejuk. So because of that, the roles have reversed. The hot air now belongs to the sea, and hot air always goes up. The third, fourth, and the fifth is still the same. Hot air rises, low pressure. Cool air from the land moves towards the sea to replace the rising air. And it goes around and around and around and around. Okay, so this explanation is, this explanation is very important to remember lah. Okay, next one, cooling system of a car engine. Okay, this is a picture of a car engine, and as I said just now, we use water, okay, as the cooling system. You can use we use coolant. There is a specific kind of liquid actually for coolant, but generally if you use water, it's actually good enough for a few reasons. Number one, it has a high boiling point. Okay, number one, it has a high boiling point, so it does not change to gas easily. Okay, number two, it has a high specific heat capacity, so that it can absorb a lot of heat without getting hotter. Okay, and number three, it is abundant, it's economical. It means water. Okay, you can find water anywhere. Okay, unless you're at a place where diorang kena catu air lah, but you can find water anywhere, and it's cheap. Okay, so it's cheaper and it saves cost. Yeah. Okay, so this is how the system works. Sorry. I think in your module, this part over here is not really shown very clearly. Okay, you may need to copy this down. But the next page, explain how the system works. This is how the system works. Okay, so in this order, okay, this is 1. Okay, 1, 2, 3, 4. Okay, it's a 4-step process. Okay, the pumps the water into the engine block. Okay, then heat is produced by the engine, absorbed by the water. The hot water flows to the radiator and the heat is released. Okay, so the hot water comes over here, then the heat is released through the cooling fans. Okay, that's why your engine there's a fan over there to blow out all the hot air. So when the hot air is all blown out, then the same water, the temperature decrease already. Temperature decrease, the water will be pumped into the engine, okay, and water will flow and absorb all the water. Then it will be pumped out and cooled down. Then it will be pumped in, flow, absorb the water, absorb the heat. Sorry, not absorb the water. The water absorbs the heat, pump out, cool down by the cooling fan, pump in. Okay, pump into the engine. Water absorb heat. Okay, water absorb the heat, become hotter. The hot water pump out or flow out lah. Okay, flow out to the radiator, cool down by the fan. Okay, cold water flows in. How many times do you want me to repeat this? Cool water flows in, becomes hotter because it absorbs the heat from the engine. Hot water flow out, cool down by the fan, and so on and so forth. Okay, yeah lah, fine. The way I explain it is a bit like, okay, but this is how it works lah. Okay, pump the engine in the block. Sorry, pump the water in the engine block. Heat produced, absorbed by water. Hot water flows in the radiator. Heat is released through the cooler air. Okay, that flows through the cooling fans. So it's very important that if you have a car, you need to make sure that your cooling fan is working. Number two, you need to make sure there's enough water, okay, in the radiator. Okay, so that you have enough water to absorb the heat. Okay, so next time when you own a car, make sure you always check the water level in your radiator. Because the worst thing that can happen is no water to absorb the heat, and then your engine overheats. Okay, and then boom, smoke. Okay, let's talk about the house. So when you build a house, we want to find materials that are good for warm weather and also for hot weather. Now the interesting thing is, both warm and hot, the most suitable material is actually wood. Okay, sorry, kayu. Kayu is wood lah. Okay, and the reason is because wood has a high specific heat capacity and it gets hot very slowly. Okay, just like rumah-rumah kampung, houses that are made of wood, right, generally is much more cooler than houses that are made of cement. Okay, which is the house that most of us live in. Okay, so in the warm weather region, traditional houses that are built from wood, which functions as an insulator from the heat from the scorching sun. Okay, the blue color there, if you don't want to copy, it's not such a big deal, but the red color, please copy. Okay, we use wood because it has a high specific heat capacity and it gets hot slower. Okay, dia lambat menjadi panas. I'm not saying that it doesn't become hot. Okay, I'm just saying that compared to cement house lah, okay, or compared to glass house, glass house is the worst lah. Okay, but compared to cement house, wood actually takes a very long time to become hot. Okay, so it's generally still cooler in a wooden house. Okay, and likewise, in the cold climate, okay, in places where there are a lot of snow, the best material is also wood. Okay, because the heat from the fires lit in the wooden houses cannot flow out. Okay, because wood functions as a very good heat insulator. Of course, when you have heat inside the fire in the wooden house, you want to make sure that the wooden house doesn't burn down. But generally, because wood takes a very long time to get hot, and it also takes a very long time to get cold. Okay, so it functions as a good heat insulator. Okay, so you may want to think next time when you grow up, you want to think, what kind of house do I want? You may want to think of building a wooden house because it's cooler. Okay, because it's cooler on hot days and it's warmer on cold days. Okay, it's very good material to use. Okay, production of the latest materials in the construction of roof building. So this building looks quite similar to our Surya Sabah. Okay, we find that the materials on the roof, we want to use an insulating concrete roof. Okay, styrofoam boards, for example. Okay, they have high heat capacity because if the roof the material of the roof has a high specific capacity, it takes a very long time to become hotter. Okay. After a while, you will find that the same few words are going to be said. High specific capacity, long time to get hotter. Low specific capacity, faster get hotter. Okay, and so because of that, the insulating concrete roof can reduce the absorption of heat from the surroundings to reduce the temperature inside the building. Because it can terima banyak haba, okay, it can reduce the temperature inside the building. Inside the building, there are people and they're generating a lot of heat. Okay, so it absorbs the heat from the inside the building itself. Okay, these are something extra. Okay, so I will probably post a photo of this in the group. You can copy this. This is not in your module, but I just wanted to show you this. Okay, we have more windows. Okay, a good house, if you want it to be cooler, we add more windows so we get good air ventilation. Okay, interestingly, you have a triangle roof. Okay, the triangle roof has a strong pattern and it reduces the effect of strong winds. Okay, we use a wall of bricks. Okay, because bricks have low specific capacity also, not cement, bricks. Okay, and it's usually easily to release heat and it is strong lah. Okay, obviously it is strong. Kampung houses usually they are the jarak. Okay, there's always far from the ground so that there is good air ventilation. Okay, on this side, the roof is made from a strong material so that it's durable. We want it to be shiny so that it can reflect the heat. Okay, the wall has a high specific capacity so that it can release more heat and the material of the wall will be stronger. Okay, so that it can last a lot longer. All right, one last one. Outer layer of space capsule. So the space capsule, the outer layer, when it comes back into Earth, okay, that I think if you watch the movie Interstellar, you'll know this lah. Okay, so space capsule on its journey back to Earth encounters a lot of air resistance when entering the atmosphere. Okay, in space there is no air. Okay, so there's no resistance. But when it's coming back into Earth, as it enters the atmosphere, it's suddenly going to be hitting a lot of air. And because of that, there's going to be a lot of air resistance. And when there's air resistance, there's always friction. The friction causes a rise in temperature. Okay, and it will cause the space capsule to burn like this. So we want the material of the space capsule to be able to withstand that amount of heat. And we're not talking about the heat like your hair dryer kind of heat. This is like thousands and thousands of degrees Celsius. So we want it to be made of a substance that is high specific heat capacity. Okay, actually not just high, very high. Okay, the outer layer of a space capsule is made from a substance with a high specific capacity so that it will heat up slowly and it has a high melting point so that it will not melt at high temperature. Okay, because if your space capsule melts while you're coming back into Earth, you probably won't survive the trip. Okay, it needs to be able to survive the trip. Okay, all right, so your work for this weekend, okay, unfortunately okay, your work for this weekend is the rest of the module. Oh, it's pretty disappointing today. There's only 16 people here. 16 people here, and the same few people that vehemently said that we don't want night class are the same people that are not here. So annoying. Okay, so in your module, okay, there is the tutorial 4.2, right? Okay, so the tutorial 4.2, what I would like you to do, is to answer all the questions to the best ability that you can. Okay, I will definitely discuss the questions lah. Okay, I will definitely discuss the questions, but I don't think I've done this with you before, right? We've never actually done a proper module. Okay, so what happens during a module discussion lah? Okay, during a module discussion, what happens is I will show you the question on my slide and I will ask somebody to answer. Okay, and usually the somebody that answers will have to unmute themselves because I cannot see the chat unless I come back to the main page, which I usually don't lah. Okay, so you need to be ready to be able to answer verbally. Okay, so for example, okay, question number 1, what is the answer? Meryl. So Meryl, you unmute yourself and say, the answer is A, like that, or A, something like so that I can hear What is the answer? So in order for you to not embarrass yourself, okay, I suggest that you answer the questions in this module. Okay, so this is the work that I want you to do this weekend. Yeah, as best as you can lah. Okay, there are some questions in here which are a little bit tough. They are not exactly. There are questions that we haven't actually explored yet, but you know, most questions you should be able to do. Okay, so give this a try over this weekend. If you have any questions, you don't know how to answer a particular question, you know, can ask me during the weekend. Totally no problem at all. Okay.